Okay, so let's go ahead and look at the last problem. So it's a problem about multiple myeloma. This is a blood plasma cancer, and it's characterized by increased blood vessel formation, angiogenesis in the bone marrow that is a predictive factor in survival. One treatment approach used for multiple myeloma is stem cell transplantation with the patient's own stem cells. And here is the data that they've obtained, and this represents the bone marrow microvessel density for patients who had a complete response to the stem cell transplant. Okay, and the measurements were taken immediately afterwards and sometime after the response. Okay, so what's happening is when you have this disease, you're forming more blood vessels, which is bad. Okay, so we're going to do a hypothesis test at alpha equal to 0.05 to see if there's evidence that the mean bone marrow microvessel density is higher before than after. That would mean the treatment's working. All right? And I chose not to copy the data from the back of the book, from the StatCrunch. I'm just going to copy it in. So this is the same patient before and after, so we're doing a paired t-test. We're looking at the mean of the difference between two related populations. Okay, so I'm just going to go ahead and type this in real quick. There's only 7 values. Normally I like to use the data because even if there's only 7, you can mess things up when you type it in, transcription errors, but my internet connection went down for some reason, so I'm going to just do it this way. Okay, so this is my data. Okay, so now to do the hypothesis test, so what we have to go through the basics here, right? I'm going to compute a few statistics, okay? So I'm going to compute some statistics here for my sample. Statistics. Okay, the first is X is, well, I'm going to actually take the difference here, right? I have to take the difference. So I'm going to take the first minus the second. Okay, and then just drag this down. So remember, this is x1 bar. This is x1 minus x2. Okay. So now I want a couple things here. I want d bar. Okay. I want the standard deviation of d bar, and I want the sample size. So let's take this off. So this is going to be the mean of the differences. This is what we do when we have a paired t-test. Okay. Notice that it's positive, and that's good because we're testing to see if this statistic's going to be positive. So that's good. I'm going to take the sample standard deviation, also of these differences, and n is equal to 7. Okay, so these are going to be the values that I actually work with. Okay, let's go ahead and do the hypothesis test. So the first thing we have to do is we have to state our hypotheses. Oops. Make this a little bit bigger. So the null hypothesis, since we're doing a one-way test, is that mu of d is going to be less than or equal to 0. Okay. And the alternative, what we're testing to see, is if the mean of the differences is positive. So we're doing a one-tailed, an upper one-tailed test. Okay, second thing I want to do is I want to compute the test statistic. It's actually very easy for this one because the t statistic, so remember t is just equal to d bar minus d naught divided by standard deviation of d divided by the square root of n. And we have to be careful when we do this in Excel. We actually have to put a double parenthesis. Some of you didn't do this. and you won't do the mathematics correctly if you don't. So let's go ahead and do that. So this is easy enough to do because I have all these values up here divided by, and now I'm going to put a pair of parentheses down here. So this is going to be this divided by the square root of n. And there's my test statistic, and that looks reasonable. Okay, that's a reasonable value for a t-score between plus or minus, 3 or 4. Now I'm going to compute the p-value. And I recall that here I'm doing I know that t is distributed. So let's write down a few things that we actually know here. We know that t comes from a t distribution with n minus 1, or 6 degrees of freedom, and we're doing an upper one-tailed test. And that's important because this test statistic is positive, therefore I'm going to have to look at the upper percentile. So the p-value here is going to be the upper percentile. It's going to be 1 minus t dot dist. There's my value. My degrees of freedom is n minus 1, and this is going to be true. And that looks reasonable. Okay. Now we're ready to make our statistical decision. So we're going to apply the decision rule. And so our decision rule here, we know that p is equal to 0.06, I'm going to round this off, which is greater than or equal to 0.05, which is equal to alpha. So this means I will fail to reject the null hypothesis. And so last but not least, we have to state our conclusions. And so we're going to say at a significance level, of 0.05, so what are we doing? Well, we're failing to reject H naught. Okay, so we're saying that there's no evidence. So there's no evidence to support, or there's not enough evidence to support the alternative. So we conclude there is not sufficient evidence and I don't like to have two concludes. So we could say that we determine, well, we could just say there is not sufficient evidence to conclude that the mean blood vessel density before treatment is higher than after. Okay, that looks good. All right, so we're done with our hypothesis test. We interpret the p-value here for part B. We're just going to say that the p-value is the probability that we could get a value this far from the mean or further. And for a one-tailed test, it's actually the probability that we could get a value this far above the mean or more. Okay. So the p-value is the percentile. The question is it really a two-sided percentile or a one-sided percentile? But I would say the correct answer to B, since we're doing a one-tailed test, is the probability that we could get a test statistic this far above 0 or further. Okay, so now we want to construct a confidence interval. Well, the confidence interval is actually very easy because it uses everything that we've done in the hypothesis test. So we want to construct a 95% confidence interval. Okay, so what do we need? Well, we need the margin of error. Well, first I'm going to put d bar. We need the value of d bar, which is just this. And let me just copy it. I'll just copy it without using the formula. So I notice that I can paste as a value. That's what I'm going to do. And round that off a little bit so it looks nice. Here we go. Okay, so now I need the margin of error. We remember that the margin of error is equal to the critical value times the estimated standard deviation of d bar. But the standard deviation of d bar is always what is in the denominator when you're doing a hypothesis test. So if we compute the critical value first, critical value is going to be the t-score for 0.05 for 6 degrees of freedom. So this is going to be t.inv of 0.05 divided by 2 with 6 degrees of freedom. Okay. And of course it's negative, but I'm going to make it positive when I do the margin of error. And the standard deviation of x bar, of d bar, is just going to be the standard deviation of d divided by the square root of n. Divided by the square root of n. We already computed that actually. So this is just equals to, and I can scroll up here and still see what I'm doing in the bar, this divided by the square root of this. There we go. Alright, so it's rather large. Okay, so now my margin of error is just the product of these two. So this is going to be equal to, and I'm going to take the absolute value now because I want this to be positive. This times this. And we're done. We know that the lower endpoint is just going to be equal to d bar minus the margin of error. Okay, so this is going to be equal to this minus this. And the upper endpoint is going to be just d bar plus the margin of error. And I'm just going to cut and paste and hit enter and go down here and change this to positive. Okay. Now notice something interesting. We did not reject the null hypothesis. So remember, when we failed to reject the null hypothesis, this value right here, okay, the book would call this D, and there's a lot of D's floating around, so it gets to be kind of crazy, but this is essentially the thing that we're testing the mean against. It's an actual number. That number has to be in the confidence interval. So when we fail to reject, the 0 has to be in here, and we see this. If we hadn't, we would know we had done something wrong, and we'd have to go back and check things out. Okay, that's all for the last problem.